Now let's take a look at part C of the problem. So part C, what are we asked to do here? They say, given that the loss X was at least C, what is the probability that the storm was of strength 1? So recall that we used N to denote storm strength. So what we have here is, well, given that the loss, so what do we want to find? We want to find, given that the loss was at least C, so that's greater than equal to C, what is the probability that the storm strength was of strength 1, so that the storm strength N was equal to 1. So this is what we want to find. Now, what we can start by doing is think a little bit about what do we know. So what do we know by this point? Well, we know the distribution of X. We have its density, and hence we can also find its distribution function. What else do we know? Well, we also know the conditional distributions of X. So the distribution of X given N equals something something, we also know that. What don't we know? Well, we don't know the distribution of N, but in fact, knowing these two things is enough to help us out. So let's just try to start by writing up the definition of a conditional probability here. So what do we have? Well, we want to find the probability that N is equal to 1 given X is greater than equal to C. So by definition, this is equal to the probability that N is equal to 1 and X greater than equal to C, so the probability of the intersection of the two events, divided by the probability that X is greater than equal to C. So this is by definition of conditional probabilities that we have this. Now, what do we know? Well, the denominator, it's good, right? Because for that we only need the distribution of X, and we have that. But the numerator is not as good because we don't know the exact joint distributions of N and X. But what we do know is that I can write the joint distribution up using conditional distributions, and what we do know is the conditional distribution of X given N. So again, we just recall the formula that the probability of one thing conditioned on another is equal to their joint probability divided by, not joint probability, is equal to the probability of their intersection divided by the probability of whatever we condition on. But however, if I isolate this probability of their intersection, then what I have is the probability of A given B multiplied by the probability of B, right? But on the other hand, I mean, it's also totally okay if I think of it as the probability of B given A multiplied by the probability of A. There's something symmetric here. And this results in what is actually called Bayes' formula, because if I take this, and I plug it into the probability of A intersected with B, then I get Bayes' formula, which tells me the following. So what does Bayes' formula tell me? Bayes' formula tells me that the probability of A given B can be written as the probability of B given A multiplied by the ratio of probability of A and the probability of B. And I can use that here because here I can just write this probability of the intersection of these two as the probability of x being greater than or equal to c given n is equal to 1, and then multiplied by the ratio of probabilities n equal 1 divided by the probability x greater than or equal to c. Now, we might recall that the probability that n is equal to 1 is just the point probability, right? So the probability that the strength of the storm is 1 is just P1. So we have that. So now the only things we need to find are the probability that x greater than c given n is equal to 1 and the unconditional probability of x being greater than or equal to c. And after we do that, we have finished this exercise. Now I feel tempted to let you guys figure the rest out on your own because it's not that hard, but just for good measure, we should probably calculate the two things together. So let's just start by doing the probability of x being greater than or equal to c. No, you know what? Let's start by the conditional probability here. Okay, so what we know is that given n equals 1, then x is exponentially distributed with parameter lambda 1. Let me just write that here. So given n equals 1, x is exponentially distributed with parameter lambda 1. And that means that to find this probability, what I can do is I can integrate the density of x given n equal 1 from c to infinity. And that density is exactly the exponential density with parameter lambda 1, which is given by lambda 1 multiplied by e to the minus lambda 1 x dx. And after I figure that out, that is, well, the antiderivative here is minus e to the minus lambda 1 x, which I will evaluate in the bounds infinity and c, and this will give me e to the minus lambda 1 c. So that was the numerator, and now we will take the denominator, running out of colors here. So the denominator, which color should I use? Let's take a red. So the denominator, probability that x is greater than or equal to c, is calculated in the exact same way, where we just use the density of x. And the density of x was what we found in part A as the weighted average of the conditional densities. And that is the sum of Pn multiplied by lambda n e to the minus lambda n x for n ranging from 1 to 3 dx. And we can interchange sum and integral. And I can also take the Pn outside here. And what I have inside is the integral of some exponential density from c to infinity. And actually we just calculated that above. So the result of this for the denominator is the sum from 1 to 3 of Pn multiplied by each of these, and that is e to the minus lambda in c. So the survival function of x is just the weighted average of survival functions in the conditional cases. And that leads us to our conclusion. So in conclusion, what was it we wanted to calculate? We wanted to find the probability of the storm strength being equal to 1, given that the loss is greater than or equal to c. So in conclusion, the probability that n is equal to 1, given that x is greater than or equal to c, is given by P1 multiplied by the conditional survival function here, which is e to the minus lambda 1c, divided by this, which is the sum from 1 to 3 of Pn multiplied by e to the minus lambda n c. So that was exercise 2-4. A pretty long exercise if you want to just understand everything that's going on. And it will also be solvable in the chapter 4 setup, which isn't what we have done here. I will leave the chapter 4 things for chapter 4. But I mentioned in the course homepage, I think, that this exercise has to do with mixture distributions, that the setup we're presented with is the classical mixture distribution setup. And that is also why there will be a video about mixture distributions on the site that you can look at. And in that video, we will use the setup from this exercise as a learning example. So for mixture distributions, keep an eye on the chapter 4 videos. When they come, there will be an example involving this exercise.